we will discuss the proof of the existence of a basis for an arbitrary vector space, in particular infinite dimensional vector spaces, and we will discuss some interesting applications of this result. So let's begin by stating our main theorem, which will be quite general. So let V be a vector space with field of scalars denoted by small k, and let A in V be any linearly independent subset. So I'll abbreviate linearly independent just by L dot I dot. Then A can be extended to a basis of the vector space. So maybe we might want to recall what the definition of linearly independent and basis is. So linearly independent means that the only way to get the zero vector as a linear combination, so let's say I have a set A as a linear independent, the only way to get the zero vector as a linear combination of vectors from the set A, so I equals 1 to n, and you have picked vectors v1 up to vn in A, is that if all the coefficients are 0. So the way to memorize that is to say the only way to get the zero vector as a linear combination from vectors from the set A is in the trivial way. Now a set is a basis, so let's say a set B is a basis if it is both linearly independent and it spans, which means that every vector in the vector space V is a linear combination of vectors from the set B. Of course, one special case of this is that, so this is like an example, we can actually apply the theorem to A is the empty set, and then the theorem tells us that V has a basis, which, even though for finite dimensional vector spaces follows essentially from the definition of what it means to be finite dimensional and some considerations there, while for infinite dimensional vector spaces this is a pretty non-trivial fact. So as a first consequence, we can conclude that if you take a non-zero vector in a vector space, and notice if V is not the zero space, then such a non-zero vector exists. So if we have this, then there exists a linear map from the vector space, let me call that map phi, from the vector field into the field of scalars, such that this linear map maps that vector to 1. In particular, we will always use that 1 is not 0. And that is a thing that follows for every field. I mean, we know that that's in the axioms of a field. So how do we prove that? Well, you just extend the set which consists just of the vector V to a basis alpha of the vector space V, and then you define phi of V to be 1, and phi of W, let's say, to be 0 for all W in my basis alpha which are not V. And and that works because we actually know that we can define linear maps on vector spaces in the very general setting, I mean by just telling what these linear maps are supposed to do on a basis. Notice that this phi here will be an element in what we call V star, the dual, and so it detects a non-zero vector. Every non-zero vector in a vector space can be detected by a functional. This is what this means. And the important thing here, this technique, like using a basis, is a technique that is often called linear extension in vector spaces. So if I have given a basis, then I can extend that. And what's the idea behind it? Just to remind you of it, I can write every vector in a unique way as a linear combination of basis vectors. So if I have already told you what the phi of the i's are, then if I want to define the linear map, I know I will have to define it as phi of x is the sum I equals 1 to n ai phi of vi. So these are given, then this will define phi of x. Of course, that this is still making perfect sense has to be proven so that this phi then defines a linear map. But we assume that this already has been done. So let me state a corollary 2, which is really a corollary of corollary 1 and not a direct consequence of our theorem. Remember that we have a map rho from V into the bidual vector space. So that's the linear space of linear maps from V star into the field K. And this map is defined by rho. If I apply that to a vector V, well, I would get an element in V star star, so linear map from V star to K. If I have to tell you how I apply that to an element in V star, so that itself is a linear map from V to K, and this is defined to be phi of V. And let's assume we know already that this is a linear map, and then the claim is that rho is monic, which means it's also injective. So monic means injective and linear, but I will actually use corollary 1 just to prove that it's injective here. So how do you prove that? Well, suppose it is not. So this is a proof by contradiction. Suppose rho is not injective. Well, then it has something in the kernel. We assume that it's linear. So suppose rho is not injective. So then there exists a vector V in my vector space V, which is not 0, which is mapped by rho to 0. So rho of V is equal to 0. Well, rho of V is an element in V star star. So a map, it's itself a map, right? It's a map from V star to K. So this being 0 means it's got to be 0 for all possible inputs. So this means for every phi in V star, every functional on V, rho of V applied to phi has to be equal to 0. But remember, this is by definition just phi of V. And that would mean that every functional on V that you take will have to vanish of the vector V. But by corollary 1, we know there exists for every non-zero vector V a phi in V star such that phi of V is equal to 1 and so is not 0. And so we get our contradiction and the injectivity of this map. So maybe because it's so much fun, to use such a strong theorem, let's say we have a subspace of a vector space V. So this is a subspace. And let's say I have given a phi in W star. So this is a functional on W. So remember what we actually have is we have this phi here, which maps from W to our field K. Then what our theorem will say, then we can find an extension of this functional to the vector space V. So there exists a phi tilde in V star which restricts So if you take phi tilde and restrict it to W, you get phi. So in this picture, what this theorem is telling, I can always extend the functional defined on a subspace to the full vector space. And what is the proof of that? Well, what we do is we start with a basis, let's say beta, a basis for W, and that's of course a linearly independent set in W, so it will be linear independent in V, and by our main theorem we can extend to a basis, let's call this alpha, of the vector space V. And now what I do is I just define phi tilde from the vector space V to K by saying, okay, phi tilde of a vector, let's say V, is equal to phi of V, as long as phi V is in a basis element for W. That will actually automatically, because beta is a basis for W, every vector in W is a linear combination of these basis vectors, that will automatically kind of like give us this condition on restricting, that if I restrict phi tilde to W, I will actually get phi, and I will define phi tilde of V to be 0, let's say, if V is in alpha and is not in beta. And so we know this defines a functional on V, and it will extend phi. So to prepare the proof, I have to remind you of the notion of a partial order on a set. So let's say our set is not empty, and a partial order is a particular relation. Remember, a relation is a subset of S cross S. So the subset is called a partial order. Well, if it satisfies three conditions, and we will not kind of like use A comma B being in the relation. Instead of that, we will write A is less than or equal to B. If the following three conditions hold, A is less than or equal to A, so A comma A is always in the relation, and if A is less than or equal to B, and B is less than or equal to C, then this will imply A is less than or equal to C, and last but not least, A less than or equal to B, and B less than or equal to A. That will imply that A is equal to B. So this, of course, is just an abstraction of what we know of the usual order, maybe on the integers or on the real number. So two elements A and B will be called comparable if A less than or equal to B, or B less than or equal to A. Partial order is distinguished from what is sometimes called a total order. If you have a total order on a set, if actually any two elements are comparable. So you talk about a total ordered set, totally ordered, or sometimes called simply ordered, if any two elements, so if every pair of elements is comparable, which, as you will see, in many situations is not necessarily the case, even though it is the case for ordered sets that you might be more used to, like the integers or the real numbers. So we will need the notion of a maximal element in a partially ordered set. So I will say that an element A0 in S is maximal, so S is a partially ordered set, if all elements which are comparable to A0 are less than or equal. So if A is less than or equal to A0 for all comparable, that's kind of important, A in my set S. So a better way maybe to think about it, to say that or there does not exist an A in S which is bigger than A naught. Where that, of course, I mean, bigger is, I mean, that means it's A naught is less than or equal to A and different from A, right? I mean, that's kind of like something that you typically do. But it's sometimes nicer to think of a maximal element in the sense that there is no element that is larger with respect to the given partial order. Let me give some examples. If you take the integers, so for S is the integers, with the usual ordering, then there's no maximal element, right? Whenever you take an integer, you will find a larger integer. This is actually one of the main properties of the ordering on the integers. Let's take for the set S, the set of all pairs of points in the plane. So let's say these are in R2, such that x2 is less than or equal to 0. Of course, points in the plane usually are not ordered, but we can just define a partial order by saying x1, x2, let's say, is less than or equal to x1 prime, x2 prime. So we say by definition, if and only if actually the first coordinates coincide and the second coordinate x2 is less than or equal to the second coordinate x2 prime. So if you think about how that looks like in the plane, right, so here we have R2, the set S is just the lower half plane, and if we look at such a ray, I mean, so if we fix some value of x1, then these elements on this piece are all comparable with respect to the usual ordering on that half line. But I mean, if you this actually will not be comparable with any points on any of the other lines. So you see there are plenty of not comparable elements in here. And if you ask yourself, where are the maximal elements in here? Well, actually, all points with x2 equal to 0 are maximal. Because whenever you have this point, right, I mean, you have now an x1, say an x1 comma 0, right, then this is comparable only to the elements on this half line below. And there's nothing bigger that is comparable to that element. So these are all maximal. So this just to show you that you have to be careful, in particular, I mean, when we're not talking about a total order. So we will need one more concept. So if you have a subset T of our set S, let's say it's not empty, and then I will call an element B0 in S, so this element will not necessarily be in T. You will call such an element an upper bound for T. This is my definition here. If every element B in T is less than or equal to that element B naught for all B in T. So here you see, typical example is we have the real line, right, and then there are plenty of upper bounds. I mean, we know that, and upper bounds do not necessarily have to be in the set, even though, I mean, in fact, actually, like typical open intervals on the real line, which are bounded above, and so they have upper bounds, but the upper bounds are not necessarily in the set. So we're now ready to actually state Zorn's lemma. So that's again a very general statement. So if we take S any partially ordered set, and let's assume that, so we assume that every simply ordered subset, so if you forgot what simply ordered means, that means that any two elements in that subset are comparable to each other. So every simply ordered subset has an upper bound. So that upper bound is not necessarily contained in that subset. An element in that subset, it might be in the bigger set. It's an upper bound. Then S contains a maximal element. Remember, maximal means there's nothing bigger. The way this is used, the way maybe to remember that, how that is used, is for our notions that if you have a maximal linear independent set in a vector space, well, there's nothing that is bigger. So if that set will not span the vector space, and that will be the main idea, there will be an element outside, and you can add it to the set and create a bigger. Partial order will have something to do with actually being a subset of something. A bigger set, which is still linearly independent, which would then contradict the maximality. That's the main argument here, but let's spell that out in more detail. So let's go to the proof of the theorem. Remember, what we have to do is we have to start with a linearly independent subset in a vector space, and we have to extend that to a basis. So I will define a suitable set S. It will be the set of all subsets of my vector space V, which are both linearly independent. So S is linearly independent, and S contains the set A, which is given, the linearly ordered set, the linearly independent set A. So now I can define a partial order on this set S by saying that one subset of V is less than or equal to another subset by definition if and only if S1 is just a subset of S2. So both are subsets of V, and I will say one is less than or equal to the other one if it is contained in it. So now in order to apply Zorn's lemma, we need to prove the assumption of Zorn's lemma, and that was that if I take any simply ordered subset, sometimes also called a chain, take any simply ordered subset, T in S, that this has an upper bound. So let this be simply ordered, which, remember, that meant any two elements there are comparable. So if you pick any two elements in big T, the first one is a subset of the second one, or the second one is a subset of the first one. And what we do now is we look at the union over all the sets T, over all T and T, and we call this set U. And of course our goal is to prove that U is an upper bound. In order to be an upper bound, we have to show that U is in the set big S. So this means we have to check two things. Well, U certainly contains A, because each of the sets T in that chain contains A. But we still now have to prove the claim, and that's the main thing. U is linearly independent. So how do we do that? Well, we start by picking M elements in U, as usual. We assume that we have a linear combination with coefficients from K, and this is equal to 0. So the AIs are in K, and we have to prove that all the coefficients are 0. Now, look at any of these vectors UI. Well, for each of these vectors ui, I know it will be an element in ti for some set that I called ti in my chain T. And so I claim if you take all these sets that you get now, T1 up to Tm, then there is a tau in T such that this tau is actually bigger than or equal to Ti for I equals 1 to m. Well, this argument is something that is typical for a chain, right? I mean, this tau is practically the T max, if you want, among the T1 up to Tm that you see there. If you have now m elements, you can kind of like sort through them, and you just can pick the biggest one with respect to the partial order, because, well, any two there are comparable. So now we're almost done, because now, so that means that now we have all the elements u1 up to um. Remember, each of these ui's is in ti, right? So ui is an element in ti, but ti is a subset of this tau, so all these elements will be elements of this tau. But this tau is an element of big T, and T is a subset of S. So this tau is linearly independent. And so I have actually a linear combination of elements from a set which is linearly independent. And so this means that all the coefficients a1 up to am are 0. And that's what I wanted to show. So we have now shown that every simply ordered subset of S has an upper bound. So now that means we can apply Zorn's lemma. So let me do that on a different slide. So to finish the proof of the theorem, so we now, there exists some S naught in S, and I will remind you of what that set S was. The set big S was the set of all linearly independent subsets of our vector space, which contain the set A. So S naught will contain A, and it will be a linearly independent set. But of course, Zorn's lemma now tells us that this is maximal with respect to the partial order, which means there's no larger element in the set big S. So the claim now is that this maximality automatically gives us that S0 or S0 also spans. And if it's doing that, it will be a basis. So that will imply this set S0 is a basis. So suppose it does not span. So again, you do an argument by contradiction. Suppose S0 does not span. Well, if that is the case, I can find a vector. So there exists a vector W in V, and this vector W is not in this set S0. But then we had that argument a lot before. If you take the set which contains just this element W and you add it to S0, you get a set which of course contains S0, which is bigger. It also contains A, and it still will be linearly independent. Remember, if it would be linearly dependent, there would be a linear relation between them, and then you look at the coefficient for this additional element W, and that would have to be non-zero, otherwise you would get a contradiction to the set S0 being linearly independent, and then you could actually solve. You can divide by that coefficient, and you're gonna see that you get a contradiction. So that means that this bigger set is still linearly independent, but that's a contradiction to the maximality. And this finishes the proof.